Hi everyone, welcome to our talk. Today we are going to talk about malware comparison and see how we got from Machoke, a small algorithm we developed in 2012, to Machoke, an algorithm in 2025. So we are Stefan and Tristan. We are working at Exatrack, a small company focused on finding unknown attackers during incident response, threat hunting, or threat intelligence. And today we are going to talk about three Pokemon for once. So the first is Machoke, a CFG hashing algorithm we published a while back. How we evolved this algorithm into Machoke, and then Zubat, a new algorithm designed to find functions in a corpus of binaries. So I think everyone here who has done malware analysis did have some of the challenges we have here. For example, when someone comes to your desk with a USB key and say, I have 100 samples and I did them reversed for yesterday. And it's like 6 o'clock. So the questions we ask often is, do I already know this sample? It can be easy to answer with just a simple SHA-256 hash. But if it's just only a little bit mutated, you don't know the sample. Does this sample belong to a known family? Does it look like something I know already? If it looks like something I already know, what's new in this sample? What's different? Or does it share some function with older ones? So to answer these questions, we developed the Machoke hash at NC, and we published in 2015 at STIC. This algorithm was able to compare hundreds of malware in a few seconds. However, we discovered that it doesn't scale to a larger data set, such as a million of samples, and we wanted to go deeper in our analysis. So first, I'm going to describe what is Machoke, because it's not only a Pokemon. The objective of the algorithm was to be simple to calculate, because we don't have much time, and we are not full-time developers. It must be resistant to small changes. The objective was to detect when a sample was just slightly updated, like when an attacker just updates the C2 address in a sample, the rest of the code doesn't change. So to calculate this hash, we extract the summary of each function in a sample. We disassemble it, we regenerate the CFG, the control flow graph, and one thing we take into account is, does it have inner call instructions? We take this textual representation and we hash it to make it smaller. The process will look like this. We have here a disassembled function, which we simplify in only the blocks with their numbers, and if there is a call instruction inside. Then we translate it into text, like the number of the block, which blocks it points to, and does it have a call instruction inside. Then we hash this with murmur hash 3, and we generate a value based on the address of the function concatenated to the hash obtained. To calculate the whole hash of a sample, we just repeat this process for each function in the binary. So we have a big list with all function addresses and all calculated Machoke hashes inside. To calculate the similarity between two samples, we just calculate a Jaka distance between the two sets of hashes, and we estimated, like during all tries, like 80% match is sufficient to say that two samples are similar. We use this algorithm with many successes for malware clustering, which was the obvious initial goal, to identify unknown samples, but also to propagate like function names or labels between malware samples, which we already had reversed when we had a new sample. You don't want to reverse each function in it. It was also used out of malware analysis for identification of shared libraries between firmwares, or identifying what was new in a firmware. And mostly we were also surprised by the numbers of people using this algorithm, because we just published it like, yeah, we're using it, if you like it, please use it. And then we saw a number of publications about it. We also discovered it has limitations, because if two samples embed big static libraries, such as OpenSSL. The two samples can match even if the code, which is not OpenSSL, is different. We also discovered that if a sample has like 100 small functions of one block, it does match, because one block, you have always the same hash, but the samples are different. And if you want to compare like 10,000 samples, you have to compare each set of hashes for the 10,000 of samples, and you have a lot of calculation to do, and it's not fast enough. That's why we will introduce Machoke.
So with Machoke, this is cool because we can compare a data set with a limited size. But when we want to scale up, this is a real problem because we have an exponential time of calculation. This is because when we try to compare a hash, a sample, we will try to find all suite of hashes in all other samples we have. So this is an exponential time of calculation, and this is not good. The solution we find is to use a bitmap. Bitmap have a restricted area, so with it, we can have a linear time to define those bitmaps. So with Machoke hashes, we will increase the point in our bitmap. You can see here, for each hash, we increase the point. When we want to compare two bitmaps, we just do a subtraction between them. So, if you have two different bitmaps, the maximum distance is the sum of those two bitmaps. Here, we have two bitmaps with 7 points, so the maximum distance is 14. You can see a blue point. The blue point is just a different value on the node, on the point. So here, when we subtract those two maps, we obtain a third with 2 points and 1 half point, so 2.5 of difference. Those bitmaps are similar to 82%. Cool. We now have the capacity to compare thousands of bitmaps with a linear time. This accelerates our comparisons, but it's always too slow for a big data set. It's because for each bitmap, we need to compare it with all our data set, all other bitmaps. This is not really useful. So the solution is to clusterize our data. For example, the first layer is just a counting of functions. When we have a sample with 100 functions, it can't match to 80% with another with 50 functions. It's not possible. So the first layer of clusterization is to count functions we have in each sample. We add a second layer of clusterization that a reduction of our bitmap density to create small heat maps representing the global density of the sample bitmap. You can see here our 3 steps. The first is the function count, the second, the small heat map, and the third, list of bitmaps for the heat map. With a heat map, we will have a clusterization with similar entropy in the bitmap. You can see those 2 first bitmaps, they are a similar repartition of points, and the third is totally different. So we see the heat map, we know that, for example, the first can't match with the third, and we don't compare them. We just compare with similar or bitmaps with a proximity. So we have 3 steps in Machoke filtering. We list functions and count them. We reduce to an heat map, and the third layer, we compare each bitmap in this subcluster of the subset of our dataset.
However, we still have some problems. The samples still share static libraries, such as OpenSSL. The compilers always include, mostly, always include runtimes in the output binaries. And also, since 2012 and 2015, there is a lot more like all-in-one binaries, such as Go compiled ones. And these kind of binaries do include like 80% of runtime or public libraries or so on, which can like hinder the similarity analysis. So we tried to solve this problem. For this, we just took a whole lot of benign samples, libraries and so on. We extracted, we calculated the bitmaps using the Machoke algorithm for each one of them. And then when we analyze the new malware, we compare with the extracted runtime bitmap, and we subtract it from the output bitmap, which leads to the output bitmap of the malware being only malware code. So for example, our generation process goes like this. We take like 3 samples of Go compiled binaries, which we know are safe, and then we generate a bitmap from it, which we will subtract from each sample we analyze, when it matches, of course. So now it's demo time. I hope it works. So we used this technique in our platform, and we used it with like 150K samples. We found some interesting matches. For example, here we have 2 sysjokers matches from another sample. The 2 new samples are separated by 8 months of development. And another one is Malware, which I know quite well. It's a malware used by CN actors. We published about it, and some other companies also found updates of this one. However, we also found an undetected version. So I'm going to see if I can use this mouse. Like computing is hard. So we just want to find similar samples to this sample, which is like Malware. VirusTotal says it's a malware. Yeah. So in our 150K samples, we only have like 10 matches, and from 99%, which is almost the same sample, to 73%, which is a resemblance, but not exactly the same. So if we took in the middle to this one, and then we want to check on VirusTotal if it's detected, we see it's not. However, during our analysis, we confirmed it's almost exactly the same. It's the same family. It's also a Malware sample, and so on. So it works. If you want the hashes, go for it.
Okay, it's cool. Now we can compare tons of samples. This is really good, but each time we compare sum of functions with all other sum of functions. What I would like to do is to find if one function is present in another sample in my dataset. This is a real different research because we don't have a repartition of points to match. We have just a function to find in all other the dataset. So we develop a specific algorithm named Zobat to go deeper in malware tracking. How we do that? We disassemble and reconstruct the control flow graph of each function. And after, we extract the main logic and build an intermediate representation of the function. We extract and isolate those features of independent logic blocks. After that, we transform each feature in a fuzzy hashing string. You have an example here. So you have a function with a simple loop. We see that there are some features, a create file, a read file, a loop, and a return. For each of those features, we generate a little fuzzy hashing. And all those fuzzy hashes will be concatenated to obtain a final hash. This final hash can be searched in all our database. One example of our test, we have some millions of functions indexed. We found this function. We see that 4 blocks have been added, and we have a match of 74% between those two functions. This is true functions of the shell. And what's interesting in the first is 42 bits, and the second 64 bits. And we have a big match between them. Actually, we didn't have false positive with this technique, maybe later. It works in real world with a lot of functions indexed.
So to conclude this presentation, code similarity is complex, but it's really useful as malware analysts. Using Machoke and Machoke at the time, we found some relations between new attackers' code and their variants. And code matching can also help a lot during reverse engineering, like I want to find this specific function, which sample does share it, and so on. But also the problems we encountered is that when you want to diff a large data set of malware, you also have to take into account the, I would say, even bigger data set of benign samples you can find, and it can cause some problems. Thank you for your attention. If you have any questions, if we have time.
There's one in our front.
Yeah, one in front.
Thank you for the presentation, guys. Very interesting, nice Pokemons. I have a question regarding your last part when you focus on search of specific function. You said you discover the main functionality, make a hash for, let's say, a part of the CFG. How do you identify what is main there? Can it be automated at all?
We extract some n-grams of the hash, index it, and after it, we can identify a similar hash in all our dataset. The problem is always to have those binaries in our dataset.
Sorry, just to clarify, my question was not like how you technically convert this, but do you need a human being to tell that this is the core functionality, I want to search for this function and related basic blocks, so go and search for this?
We train in reality, we have 2 datasets, one of benign functions and one with malwares. And all functions in benign dataset will subtract those malware datasets. So this is to avoid replication of code sharing with good wares. But sometimes we have run times that match anyway.
Got it. Thank you. Let's take it offline, maybe.
Thank you.
Thank you. A very quick question to conclude.
If you have 2 hashes that are very similar or very different, with this other capability of looking at different functions, are you able then to say these 2 samples have these functions in common and these functions that are different?
Even with the Machoke hash we published in 2015, we can say in a sample like, this function is shared because it has exactly the same hash. We also had some heuristics, like if I have 3 functions in a sequence, and the 2 on top and below do not have changed, maybe only one in the middle have changed. But it worked for matching samples, so I don't know for completely different samples. For this, we will use Zubat to find like a specific function in the samples.
Okay, thank you very much.
Thank you.
So I need a few seconds